Far out in the Pacific Ocean, a remarkable discovery has captured the attention of scientists and the public alike. Researchers announced that they had found tiny metallic fragments on the ocean floor that may have come from beyond our solar system. The project was led by Avi Loeb, a well-known astrophysicist from Harvard University. Soon after, rumors began to spread that Harvard had held an emergency meeting because of what was discovered deep in the Pacific Ocean. But what really happened? Let's find out the complete truth. It all began on January 8, 2014, when a bright fireball streaked across the night sky above the Pacific Ocean, northwest of Manus Island near Papua New Guinea. The event was detected by the U.S. Department of Defense sensors, which constantly monitor the atmosphere for high-energy flashes. These same sensors were originally created to detect nuclear explosions. When scientists later studied the data, they realized this wasn't just an ordinary meteor. The object was officially listed as CNEOS January 8, 2014 and later came to be known as Interstellar Meteor 1, or IM-1 for short. What made IM-1 stand out was its extreme speed. The meteor was moving at about 45 kilometers per second relative to Earth, and more than 60 kilometers per second in relation to the Sun. That's far faster than most meteors that enter Earth's atmosphere, which are typically trapped by the Sun's gravity. The path of IM-1 showed something very unusual. It was moving on a hyperbolic trajectory. This means it wasn't bound by the Sun's gravity and had likely come from beyond our solar system. In simple terms, this object wasn't just another space rock, it was a visitor from another star system. For several years, this discovery remained hidden from the public. It wasn't until 2019 that Avi Loeb, who is the Frank B. Baird Jr. Professor of Science at Harvard, and his student Amir Siraj, came across the data again. They were reviewing NASA's public meteor database when they noticed something strange. The recorded speed of the 2014 meteor was so high that it exceeded the Sun's escape velocity. This meant it wasn't from within our solar system. Loeb and Siraj wrote a scientific paper suggesting that the meteor was the first interstellar object ever detected in our solar system, years before the famous interstellar object Oumuamua was discovered in 2017. However, their claim couldn't be fully confirmed at the time because parts of the government data used to calculate the meteor's speed were still classified. Without access to that information, their paper couldn't be peer-reviewed or officially accepted by the scientific community. The research remained in limbo, waiting for proof. That proof finally came years later. On April 6, 2022, the United States Space Command released an official, unclassified memo signed by Lieutenant General John E. Shaw. The memo, sent to NASA's Planetary Defense Coordination Office, stated with 99.999% confidence that the meteor's velocity was high enough to indicate an interstellar trajectory. This meant the U.S. government had officially confirmed what Loeb and Siraj had claimed all along: IM-1 came from outside our solar system. This confirmation made IM-1 the first officially recognized interstellar meteor in human history. When the meteor entered Earth's atmosphere, it released energy equal to about 110 tons of TNT. It exploded roughly 18 kilometers above the ocean surface, scattering debris across an area of about 10 square kilometers. Because the explosion happened over a remote region of the Pacific Ocean north of Papua New Guinea, there were no human witnesses and no immediate attempts to recover debris. But Avi Loeb wasn't satisfied with just the confirmation. He wanted physical evidence. He wanted to find pieces of this interstellar object and study them in a lab. So in June 2023, Loeb led a scientific expedition under the Galileo Project, a Harvard-backed research initiative focused on searching for evidence of extraterrestrial materials or technology. The goal of this mission was simple yet incredibly ambitious: to find the remains of the 2014 meteor on the ocean floor and bring them back for scientific analysis. The search area was located north of Manus Island, which is part of Papua New Guinea's Admiralty Islands, around 85 kilometers off the coast. Using a specially designed magnetic sled that could drag across the seabed, Loeb's team began to explore the impact site. They were looking for tiny metallic fragments, called spherules, that might have formed when the meteor burned up and melted while entering Earth's atmosphere. After days of careful searching, the team successfully collected dozens of microscopic metallic spheres from the ocean floor. Each was less than a millimeter in size. When these samples were brought back to the surface, they were sent to laboratories for testing. The results were fascinating. The spherules contained a unique mix of elements such as iron, nickel, and rare metals like beryllium and lanthanum. This composition did not match any known meteorite or Earth-based material, suggesting that they might have an interstellar origin. These findings immediately caused excitement in the scientific world. Some researchers said this was one of the most important space discoveries in decades. Others remained cautious, arguing that more evidence was needed to confirm whether the fragments truly came from outside our solar system. Avi Loeb welcomed all viewpoints, saying that open scientific discussion was the best way to reach the truth. He continued testing the samples to determine whether their atomic makeup could reveal a clear sign of interstellar origin. If Loeb's conclusion turns out to be right, this would mean that for the first time in history, scientists have recovered actual physical material from another star system. This discovery could help answer long-standing questions about how matter forms in other parts of the galaxy and how such objects travel through space before reaching Earth. It might even give us clues about the nature of other planetary systems. Still, many scientists have urged caution. They argue that proving something is interstellar is incredibly difficult because it requires ruling out every possible explanation from within our own solar system. Natural variations in meteor composition and the intense heat from atmospheric entry could make the fragments appear unusual even if they came from nearby space. Loeb, however, believes the evidence speaks for itself and continues to test the samples with advanced instruments capable of measuring isotopic ratios that could pinpoint their origin. Regardless of the debate, Avi Loeb's expedition has already changed how scientists think about interstellar objects. Before this, people assumed that only large bodies like Oumuamua or Comet Borisov could enter our solar system from deep space. The discovery of IM-1 shows that even tiny meteors can make that incredible journey, traveling billions of kilometers from another star before reaching Earth. Loeb plans to continue his work. He hopes to conduct more ocean expeditions in the future to search for other potential interstellar meteors recorded by U.S. defense sensors. His long-term goal is to find not only natural interstellar debris but perhaps one day, evidence of alien-made materials. While that idea might sound far-fetched, Loeb argues that science must stay open-minded and always follow the evidence. For now, the small metallic fragments recovered from the Pacific Ocean represent one of the most mysterious and potentially groundbreaking discoveries in modern astronomy, a reminder that our planet is constantly visited by messengers from the stars, and that the universe still holds countless secrets waiting to be uncovered. Using military satellite data and later calculations of the meteor's path, Avi Loeb and his team were able to narrow down the likely area where debris from the interstellar meteor had landed. Their calculations pointed to a part of the Pacific Ocean near 1 degree south latitude and 147 degrees east longitude. The seafloor there was about 1.7 kilometers deep, challenging for exploration, but still within the range of modern ocean recovery technology. After months of planning, paperwork, and discussions with Papua New Guinea's National Fisheries Authority and Maritime Safety Authority, Loeb's team received permission to conduct their research mission. For the expedition, they chartered a ship called the Silver Star from EYOS Expeditions. In mid-June 2023, the Silver Star set sail from the port of Lorengau on Manus Island, carrying 26 people, including scientists, engineers, navigators, and divers. The group included experts from Harvard University, the University of California at Berkeley, and several other research institutions. The heart of their mission was a custom-built magnetic sled, roughly 2 meters long, that was towed slowly across the seafloor. The sled was equipped with powerful neodymium magnets, underwater cameras, suction devices, and small trays to collect metallic fragments. For 2 weeks, the crew worked in carefully mapped grids, covering about 175 kilometers of total track line. The sled skimmed just a few centimeters above the ocean floor, guided by GPS and an advanced navigation system. Each time the sled was brought back on deck, the team washed, filtered, and examined the material it collected. What they found was fascinating. By the end of the mission, the scientists had recovered about 850 tiny metallic spheres. These microscopic beads ranged in size from just 0.1 millimeters to 1.3 millimeters, smaller than a grain of sand. They sparkled faintly under light, appearing as shiny black dots. Loeb's group carefully documented everything. They recorded the exact coordinates of each collection site, photographed the samples under microscopes on the ship, and stored them in sterile containers to prevent contamination. The total mass of all the recovered material was just a few grams, yet it represented something extraordinary, the first physical sample that might have come from an interstellar object. Once the Silver Star returned to port, the team immediately began analyzing the samples. At Harvard University, Loeb and his colleagues used scanning electron microscopes and X-ray fluorescence to examine the chemical composition of the spherules. More advanced tests were also conducted at the University of California at Berkeley and at Bruker Corporation Laboratories, where scientists used electron microprobes and mass spectrometers for precise measurements. The results revealed that most of the spherules were made mostly of iron, with smaller amounts of elements like magnesium, titanium, and nickel. This was consistent with what scientists would expect from metal droplets that had melted and solidified during the meteor's fiery entry through Earth's atmosphere. However, about 10% of the collected spherules stood out. These unusual samples showed a unique elemental makeup not seen in typical meteorites or any Earth-based materials. They contained higher levels of beryllium, lanthanum, and uranium, an extremely rare combination that the team labeled as Bala type. The presence of lanthanum and uranium in such ratios was especially surprising because these elements are not common in either micrometeorites or ordinary ocean sediments. This finding quickly became the main focus of further investigation. Loeb and his team wanted to understand whether this composition pointed to a natural but rare formation process, or something that might suggest an artificial origin. The physical nature of the recovered spherules also supported the idea that the meteor was unusually strong. Data from U.S. military sensors in 2014 showed that the meteor exploded at an altitude of about 18 kilometers after experiencing pressures greater than 200 megapascals. That's nearly 2 million times atmospheric pressure at sea level. Calculations of how the meteor slowed down as it entered the atmosphere indicated that the material it was made of had a strength greater than that of ordinary stony meteorites, and possibly even stronger than standard iron meteorites. This exceptional toughness would explain why fragments of it were able to survive the intense heat and pressure of atmospheric entry and eventually settle on the ocean floor as the metallic spherules later recovered. Scientists have proposed two main ideas to explain the origin of these strange particles. The more cautious theory is that IM-1 was an unusual but natural interstellar rock or metal alloy, possibly a piece of an alien planet or debris from an ancient supernova explosion. Its odd chemical mix could be the result of processes that occurred in another star system long ago. According to models of how elements form inside stars, many different metal combinations are possible depending on the life and death of the parent star. Therefore, a rare mix like beryllium, lanthanum, and uranium could still be entirely natural, even if it doesn't match anything found on Earth or in other known meteorites. This explanation fits within the limits of astrophysics and suggests that IM-1 could simply be a product of nature, a space rock born in a distant solar system, forged under conditions different from those in our own. The journey from another star system to Earth would have taken millions or even billions of years, and during that time, its surface could have been altered by cosmic radiation, collisions, and interstellar dust. When it finally crossed paths with Earth, it burned up in the atmosphere and left behind the tiny metal droplets that Loeb's team recovered from the Pacific Ocean nearly a decade later. Regardless of the exact origin, the recovered material provides scientists with an unprecedented opportunity to study matter that may have come from beyond our solar system. For decades, astronomers have only observed interstellar objects like Oumuamua or Comet Borisov from afar, but never had a chance to hold pieces of one in their hands. The tiny metallic spherules retrieved by Loeb's team could be the first direct samples of such material, a glimpse into the chemistry and structure of another world orbiting another star. Even if later studies confirm that these particles are natural, their discovery still marks a milestone in science. It proves that humans can locate and recover debris from interstellar objects, even from the depths of the ocean. And if further analysis reveals evidence of artificial design or unusual isotopic ratios, it could open an entirely new chapter in our understanding of the universe, one that connects us not only to distant stars but perhaps to other forms of intelligence beyond Earth. He believes the object might not be a natural rock at all, but technological debris, a relic crafted by another civilization and ejected from its home star system long ago. To explore this extraordinary idea, Loeb's Galileo project initiated precise isotopic studies to trace the meteor's true origin. Scientists are examining isotope ratios, such as uranium-235 to uranium-238, and variations in iron and oxygen, to determine whether the material formed under alien stellar conditions. These tests demand ultra-sensitive instruments and strict contamination controls. For now, the world can only wait for the results. Recognizing the limits of the initial surface-towed searches, Loeb's team announced a follow-up mission. This time, they plan to use the remotely operated vehicle Hercules, a deep-sea explorer operated by the Ocean Exploration Trust. Hercules can descend over 3 kilometers, hover precisely above the seafloor, map the terrain in 3D, and even grasp objects with robotic arms. The goal is to locate larger, intact fragments of the 2014 meteor, samples that could finally reveal its mineral and isotopic secrets. While Loeb's 2023 expedition captured global attention, many scientists remain cautious. Planetary researchers point out that microscopic metallic spherules like those recovered are surprisingly common in marine sediments. They can result from volcanic activity, industrial emissions, or ordinary meteoroids burning up in Earth's atmosphere. Experts such as planetary scientist Peter Jeniskens emphasize that without clear isotopic evidence, it's far too early to claim an interstellar, let alone technological, origin. The meteor's unusual Ballah composition, they suggest, might stem from seabed hydrothermal activity or industrial contamination rather than another star system. Loeb's expedition also highlighted the international dimension of such groundbreaking research. The search zone lies within Papua New Guinea's exclusive economic zone, and Loeb's team worked under official permits and local supervision to ensure environmental and maritime compliance. Operating out of the port of Lorengau, the research vessel Silver Star provided jobs and logistical coordination for local agencies, a reminder that even in the pursuit of cosmic mysteries, diplomacy and collaboration remain essential. Beyond the debate over IM-1's true nature, the expedition carries profound scientific significance. If confirmed as interstellar, these tiny spherules would represent the first tangible samples from another star system ever recovered by humans. Unlike interstellar visitors such as Oumuamua, 2017, or Tuai Borisov, 2019, which were studied only through telescopes, IM-1 offers physical material, something we can analyze here on Earth. Even if the fragments turn out to be terrestrial, Loeb's pioneering approach opens a new pathway for exploring the cosmos, using the depths of our oceans as a gateway to the stars. Statistically, IM-1's detection also implies that Earth may be struck by half-meter-sized interstellar meteors roughly once every decade, far more often than previously believed. This discovery reshapes our understanding of how matter travels between star systems, and even how life's building blocks might spread across the galaxy. It also strengthens the case for creating new global monitoring networks capable of quickly locating meteor impact sites, allowing scientists to recover fragments before ocean currents wash them away. Whether these mysterious grains turn out to be relics from a distant star system or simply rare products of Earth's own geology and industry, their discovery marks a milestone in the emerging field of interstellar archaeology, and showcases humanity's growing ability to reach beyond the solar system. Other confirmed interstellar visitors. The discovery of objects originating from outside our solar system has reshaped planetary science, and transformed our sense of just how common interstellar debris might be. The first confirmed visitor was one Oumuamua, detected on October 19, 2017, by the Pan-STARRS 1 telescope in Hawaii. Astronomers quickly realized its orbit was hyperbolic, with an eccentricity of about 1.2, proving it wasn't gravitationally bound to the Sun. Estimates placed its size between 100 and 400 meters, with an unusual shape, possibly long and cigar-like, or broad and flat like a pancake. Unlike any known comet, Oumuamua showed no visible coma or dust tail, yet its path revealed a faint but measurable non-gravitational acceleration, as if something besides gravity was pushing it. Scientists proposed natural explanations: the slow release of molecular hydrogen, a nitrogen ice fragment from a Pluto-like world, or a fluffy, fractal dust aggregate. But Avi Loeb offered a more provocative idea, that Oumuamua might be a product of intelligent design, a thin, reflective light sail, engineered to travel between stars using the pressure of starlight itself. He noted its shape, its unusual brightness variations, the absence of gas emissions, and its gentle acceleration, all consistent, he argued, with a lightweight artificial object. Loeb presented the hypothesis in scientific papers and in his 2021 book Extraterrestrial, The First Sign of Intelligent Life Beyond Earth, urging that science remain open to technological possibilities, even those that challenge convention. 2 years later, on August 30, 2019, amateur astronomer Gennady Borisov from Ukraine discovered the second confirmed interstellar object, 2I Borisov. Using a handmade 0.65-meter telescope, Borisov spotted a new comet racing toward the Sun. Follow-up observations revealed a hyperbolic orbit with an eccentricity of about 3.3 and a velocity near 32 km per second relative to the Sun. Unlike Oumuamua, Borisov looked unmistakably cometary, with a bright coma and a long tail of dust and gas. Spectroscopy showed water, carbon monoxide, and other familiar volatiles, suggesting that distant planetary systems produce comets much like those in our own Kuiper Belt and Oort cloud. With a nucleus estimated between 0.4 and 1 kilometer, Borisov proved that interstellar comets are not cosmic rarities, but part of a vast and dynamic population. The third visitor, 3I Atlas, was discovered by the Asteroid Terrestrial Impact Last Alert System in Hawaii. Its orbit was clearly hyperbolic, with an inbound speed of 25 to 30 km per second, and it displayed a diffuse coma and developing tail, hallmarks of a long-period comet. Though studied less extensively than Borisov, 3I Atlas reinforced the idea that interstellar comets are common enough to be detected regularly by modern sky surveys. These three flybys stand in sharp contrast to CNEOS January 8, 2014, the interstellar meteor known as IM-1, which entered Earth's atmosphere 4 years before Oumuamua was even spotted. Detected by U.S. Department of Defense sensors, it blazed over the Pacific Ocean near Papua New Guinea at a speed of 45 km per second, fast enough to escape the Sun's gravity. Unlike the others, IM-1 didn't just pass by, it hit Earth. Together, these four objects, Oumuamua, 2I Borisov, 3I Atlas, and IM-1, mark a dramatic shift in our view of the cosmos. Before 2017, not a single interstellar object had been confirmed. In less than a decade, astronomers have recorded 3 visitors and 1 impact. The new discoveries have inspired global efforts to catch future arrivals earlier and study them in greater detail. The Vera C. Rubin Observatory in Chile, set to begin full operations in the mid-2020s, will use its 8.4-meter mirror and 3.2 gigapixel camera to image the entire visible sky every few nights as part of the Legacy Survey of Space and Time, LSST, expected to discover many more interstellar objects each year. Meanwhile, the European Space Agency's Comet Interceptor mission aims to rendezvous with an as-yet unknown interstellar comet, meeting it as it races through the inner solar system. These missions reflect a growing consensus: interstellar objects are far more common than once believed, and each one offers a precious glimpse into the chemistry and dynamics of distant planetary systems. Avi Loeb, for his part, continues to argue that these discoveries are not just about cataloging celestial visitors, they might be the first whispers of something far greater waiting to be understood. Drawing inspiration from the zoo hypothesis, first proposed in 1973 by MIT radio astronomer John A. Ball, Avi Loeb suggests that advanced extraterrestrial civilizations might be intentionally avoiding direct contact with us while still quietly observing. Much like humans watch animals in a nature reserve without interfering with their natural behavior, such civilizations could be watching humanity from afar, allowing us to evolve and develop without disturbance. Loeb proposes that a highly advanced culture could send out autonomous probes or monitoring devices across the galaxy. These machines, traveling slowly and silently between the stars, might drift into planetary systems like ours to gather data. With the recent rise in confirmed interstellar detections, including Oumuamua in 2017, 2I Borisov in 2019, 3I Atlas in 2025, and the earlier interstellar meteor IM1 in 2014, Loeb argues that our solar system may already contain remnants or artifacts of such watchers. He finds the behavior of Oumuamua especially intriguing. The object's non-gravitational acceleration, movement that didn't fit the pattern expected from natural forces, combined with its lack of a visible tail and its brief visit, led him to suspect that it could have been artificial in nature. Its strange, elongated or pancake-like shape only deepened the mystery. For Loeb, dismissing the technological explanation outright would mean ignoring a real scientific possibility. He insists that science should remain open to all hypotheses, no matter how unconventional they may seem, as long as they are testable. In 2021, Loeb launched the Galileo Project at Harvard University, a research initiative aimed at studying interstellar objects and unidentified aerial phenomena, UAPs, using rigorous, transparent scientific methods. The project's goal is to apply the same level of investigation used in mainstream astrophysics to subjects that have often been overlooked or stigmatized. By deploying advanced telescopes, sensor arrays, and imaging systems, the Galileo project seeks to capture high-quality data that can confirm or disprove claims of extraterrestrial technology. Loeb envisions a future where scientists treat interstellar visitors not just as space rocks, but as potential probes, each carrying information, whether natural or artificial, from beyond our solar system. He advocates for building a global infrastructure capable of detecting, tracking, and analyzing the next interstellar object in real time, allowing humanity to study it up close instead of watching it slip away into the void as Oumuamua did. For Loeb, the importance of this research goes beyond proving or disproving alien technology. It represents a step toward breaking free from humanity's cosmic isolation, showing that we are finally ready to look outward with both curiosity and courage. Whether these objects are pieces of nature's handiwork or relics of intelligent design, the search itself, he believes, is an expression of what it means to be human, the desire to explore, to understand, and to know if we are truly alone. And that's it for today's exploration. If you enjoyed this deep dive into the mysteries of interstellar visitors and the bold ideas of Avi Loeb, don't forget to like, comment, and subscribe to stay updated with our latest uploads. And before you go, make sure to watch the video that's appearing on your screen right now. It's one you definitely don't want to miss.